Great to see you again. We are continuing in these presentations. Now we are going to look at recursively defined sets and structures. They're very important in computer science, so we are spending some time on defining them and identifying how we can create them and what their properties are. So what's the principle? What's the principle of recursively defined sets? We looked at the creation of recursive functions or defining functions in a recursive way. We can do the same now when we are dealing with sets. And we can also do it on structures. That will be in the next video. But here we're looking at the sets itself. Now, the same thing applies like for the recursively defined functions. We have a basis step and a recursive step. So the basis step is defining how we start with the set, and then we're going to see how we build the additional elements of that set. The basis step is that initial collection of elements, and the recursive set provides rules to form the new elements based on those already known before. So we will describe, once we have the basis step, we will say how will we find the next element from the basis step, and then we continue to use the recursive step to create more elements based on the previous steps. Now there is also what we call an exclusion rule. It may be included into the description. It's not always necessary. It can be included in the basis step, and it let's say defines what elements are included. So basically, it defines when certain elements cannot be a part of the recursively defined set. Now, even when we don't mention the exclusion rule, we assume the exclusion rule. We assume that it is applicable. So even that, we will see what can be done, what are the possibilities, and what elements cannot be part of the set. Let's look at the natural numbers and the integers. We know the natural numbers, the integers, there are two sets that we know. Now, how do we create them recursively? Now, let's have a look at the subset of the integers. We have a basis set or step where we say that 2 is an element of the set. S is a subset of the integers. And we look at the recursive step. If X is an element of S and Y is an element of S, then X plus Y is an element of S. Now, when we have 2, we have X2 is an element of S, and the only other element is also 2. So we can say 2 plus 2 is equal to 4, which is an element of this subset. We can now add 2 plus 4, because now we have also 4, so we find 6. We can say 4 plus 4 is 8, 6 plus 4 is 10, and so on. Now, what we are doing here, what we are creating here, is a subset of the natural numbers or the positive integers, which contains the multiples of 2. Now, we consider the set of the natural numbers, n0. Now, we have to say something about the natural numbers and n0. There are some different definitions about related to the natural numbers. Some include 0, some do not include 0. Originally, 0 was not included in the set of the natural numbers because they are done by counting. We can count 1 tree, but we can not count 0 trees. So typically, the extension including 0 is written by n0. So we consider here the set of natural numbers including 0. And the basis step here is 0 is an element of n0. Now, the recursive step says if n is an element of n0, then n plus 1 is an element of n0. So we start from 0. 0 is an element of n0. Now that also means that 0 plus 1 is equal to 1 is an element of n0, is an element of the natural numbers. And when we continue this and we don't stop, what do we see? We basically find the set of the natural numbers by counting. We always add one unit. And that's basically, when we go back to mathematics, it's how we originally defined the set of the natural numbers. So here we have two examples how we can recursively define some sets. These are quite simple sets, sets that we can find or define quite easily, but we have some other examples we can look at. One of the elements that is also important in computers and in discrete mathematics is about strings. Now, we look at the set of the strings, which is sigma star over the alphabet sigma. So sigma is the alphabet that we consider. And the basis step is that we have an empty string lambda, which is an element of the set of the strings sigma star. And we have a recursive step. If W is an element of sigma star, the set of the strings, and X is an element of the alphabet, then Wx is an element of sigma star. So basically what we are creating strings of letters of the alphabet. Now let's have an example. Here we consider the set of the alphabet 0 and 1. So we have the basis step where lambda is the empty set, is an element of sigma star. The recursive step, if W is an element of sigma star and X is an element of sigma, then Wx is an element of sigma star. Now, what do we find in this set? First of all, we have the empty set. We have the alphabet, we have two members, 0 and 1. So we have lambda and 0, which gives us 0. Lambda and 1 gives us 1. Then we have 0 and 0 gives us 0 and 0. Then we have 0 and 1, which gives us 0 and 1. Then I have 1 and 0, which gives us 1, 0. We have 1 and 1, and then we have 1, 1, and so on. So we continue building this set of strings based on numbers here, but we can consider them as strings too. We look at the set sigma. Now the set of the alphabet is composed of two letters A and B, and we want to see that the string AAB is an element of sigma string. Now, we know that lambda is an element of sigma string. A is an element of the set of the alphabet, so A is an element of sigma string using the recursive step. Now we have A, an element of sigma string. A is also an element of the alphabet, so we can conclude using the recursive step that AA is also an element of sigma string. The next thing we can do, we continue with the recursive step. We say that AA is an element of sigma string. We also know that B is an element of the alphabet, sigma. So we can say, using the recursive step, that AAB is an element of the set of the strings sigma star. So we have here, in fact, the recursively defined sets based on strings. Another element that we can do is to look at concatenate strings. We are, in fact, adding strings, and you can find this also as a formula in Excel. It's a very interesting formula. You can form kinds of sentences or paragraphs. You can create a lot of new data based on strings, and you can say that the formula in Excel is concatenate S1, S2 up to Sn, and S1 up to Sn are different strings. So we can create something, and we will look at some example later on. Now we consider the set of the strings sigma star over the alphabet sigma. The basic step is if W is an element of sigma string, then W times lambda is W. So we in fact, we look at that new string. And the recursive step, if W1 is an element of Z string and W2 is an element of Z, if W1 is an element of sigma star and W2 is an element of sigma star, and X is an element of the alphabet, then we can say that W1 times W2X is W1 times W2 times X. We can also write W1 times W2 as W1, W2. Now let's have a look what we can have. We can consider W1 is lucky. W2 is just a space, and W3 is Luke, my first name. And then I can say that W1, W2, W3 is, in fact, the new string Lucky Luke. We all know the series Lucky Luke, or perhaps you don't know it anymore. It's a comic series that's already very old with the cowboy called Lucky Luke. Now, my version is Lucky Luke. Another example of concatenation would be W1 is supercali, W2 is fragilistic, and W3 is expialidocious. And when we combine those three together, when we concatenate them, we find supercalifragilistic expialidocious. And some of you may remember or may know that this comes from the movie of Mary Poppins, which was a movie that was, I think, produced in the 1960s. I saw it when I was a young boy, but it's still quite famous. You can still find it on the internet and just have a look and see what it does on the movie. So I hope you enjoyed the little extract of supercalifragilisticexpialidocious. Now we are going to look at the recursive definition of the length of a string. How do we find the length of a string? Now the same thing, we can find this as a formula in Excel, is the formula len, and you select a string and it calculates the length of the string. It doesn't only calculate the number of characters, but it also considers the spaces like characters. So you can calculate, you can do some calculations with that. Now, how do we do that in discrete mathematics? And we will look at a recursive definition of the length of a string. Now, the basic step, the len of lambda is equal to 0, so the empty string has a length of 0. There are no characters, there are no elements in it, so the length is equal to 0. Now, the recursive step, len, the length of wx, is the length of w plus 1. If w is an element of the set z star, and x is an element of z, or I should put here sigma star and sigma. So they're both elements of the alphabet and the subset that we have here, the subset of the strings. Now, when we look at it, the length of the word business, so the basis step len is lambda, we can say it's equal to 0. The recursive step, we have len lambda b, so it's the length of lambda plus 1, which is equal to 1. Then we have the length of bu is the length of b plus 1, because we added one additional letter, is 2. And finally, we come recursively to the length of business, which gives us the number 8. So basically, we can define here the recursive definition of the length of a string. The next thing is looking at what we call well-formed formula in propositional logic. And it's possible to use the recursive definition of sets to define the set of well-formed formula that we can use in propositional logic. It's very important to create well-formed formula because the formula has to have a sense. There has to be some kind of logic. Now, in the formula, we consider true and false as the possible outcomes. We have propositional variables, and we have the operators which are part of the set, not, and, or, if, then, and if then are here. So we have all those elements here, all those operators in the set. So we can now start with the basic step, and we say that T and F and the propositional variable S are well-formed formulas. So we start from a basic formula. The recursive step, when we look at E and F, F is not false here, are well-formed formulas. So E and F are basically the expression of a well-formed formula. Then not E, E and F, E or F, E then F, and E then only F are well-formed formula. So basically, when we are using the basic step and the recursive step, we can create a set of formula. So basically, we know that T, F, P, and Q are well-formed formula. We look at them. P, R, Q are the propositional variables that I'm considering. And we know from the recursive step that we can say that P and Q, if P then false, if false then Q, are also well-formed formulas. And based on these well-formed formulas, we can continue with the next generation. We can say that P and Q, or if P and Q then, if P then F, false, or Q or P and Q, those are also well-formed formulas which follow the same rules as we defined in the recursive step. Now, we also have to consider one important element here, that not PQ is not a well-formed formula, because we can say not P or not Q, but not PQ. PQ is not a well-formed formula to start with, so we have to see that when we create formulas step by step using the recursive step, we see that all these formulas comply with the rule of well-formed formula. We can do the same in the operators and operands that we have. We can use them in mathematics. We consider here variables, numerals, and the operators from the set plus, minus, star, division, and the arrow to the top means power. We can say that the basic step is that x is a well-formed formula if x is a variable. X on itself is a well-formed formula. And now with the recursive step, we can say if we have two well-formed formula G and F, we can say that F plus G, F minus G, F star, F multiplied with G, F divided by G, and F to the power of G are also well-formed formula. And we can have some examples. For example, we can say that we have the variable x and y and the constant 2 and 5. Basically, they are well-formed formulae. And from the recursive step, we can say that x plus y, 2 minus x, 5 times y to the power of 5 are well-formed formulae too. That's the first iteration. And for the next iteration, we can say 2 plus x plus y, 5 times 2 minus x. So we build a new step based on the previously defined well-formed formula. Now, that was it, what I wanted to show in this video session. In the next session, we will look deeper in sets of rooted trees and extended binary trees. These are also very important in IT. We will look back at those when we will be discussing at certain algorithms. They will be based on rooted trees and binary trees or extended binary trees. So that will be in the next session, and I'm looking forward to seeing you there. Thank you and bye-bye.